Hello, hi everyone. I'm just recording a playlist on quantitative finance, and the topic that I want to start with first is stochastic processes. I am myself a year three major. I study data science and economics at NTU, so I've just been doing a lot of this math. So I feel that if I can just help some people to understand it better, that'd be really cool. So the first thing that I want to start with is stochastic processes, and all that a stochastic process means it's a random process and it's random with time, but it also just has inherent randomness, this process. And a good intuition to have for a stochastic process, what we typically start with, is a gambling process. And let me just give you the intuition for what this process actually is. So let's say that at any given time you had S dollars, and if at the next time moment, so let's say the time right now, so there's just a lot of notation in math, so I'll probably omit it for now, but I think it's a good idea to just be sort of familiar with it from time to time. But here, let's say I have an S amount of money in the next time period. If I could have S plus 1 or S minus 1. This is what a gambling process is. So with every time period, you could actually be $1 richer or $1 poorer, so to say. And you'll do this for a lot of time periods, and this is what the basic intuition of a gambling process looks like. And then we have a lot of more interesting stuff with it because you have something called boundary conditions for stochastic processes. And one notation that's been used in the textbooks that I have seen is xn, which is just defined as your wealth at time n. So it's just the amount of money that I have with myself at time n. And they could have two cases, and just always remember that this is telling you your wealth at, and this is the time index. This just helps me to like remember because there's just so much notation, so I'm just always trying to remember what it means. And at this time n plus 1, I could either be at this much money, which is, this is the amount of money that I had at time n, but now I'm at time n plus 1, so I am now $1 richer. And here I am at x n minus 1, so I'm now $1 poorer at at time n plus 1. So this happens if I want to convert this to actually probabilities. The probability that at x n plus 1 I have 0, and this is also given the fact that I had 0 to begin with, is 1, because there's 100% chance of this happening in a way, right? Like, this is how I just colloquially think about it, that this is how it's going to be, because you don't play the game at all. So this is how it's going to remain, because nobody lets you play the game, you don't have any money, right? Very similarly, uh, you take the other case wherein you say that this is where I lost the money, but I can look at the boundary cases that I have. And my boundary cases just tell me that, okay, like, if you started with 0 or if you started with S, you could have just two cases. And the above one is what I said here, but you just have a very similar one here wherein you say that, okay, that at time n plus 1, if you have S, given that you started with S, the probability of that happening is 1, because your wealth is going to maintain, because you're not going to gamble to begin with, so your wealth stays constant. And this is exactly what happened here also. So that's just a very interesting thing that happens. And now we can start analyzing these processes more and just have some a little bit more intuition about them. So the first thing that I want to talk about is just a graph that a lot of people talk about for a gambling process. So I'll also introduce a lot of the notation here, which I've already introduced before, but it just gives you an even more intuitive understanding about just what I'm saying. So this is n, and what is n? N is the time period, right? So you started with 0, and what you have here is xn, which is wealth, and you can continue to have, like, just these different things for wealth. And this was your time period, but this is your wealth here. So let's say that to begin with you had x naught equals 2, which means that I had $2 to begin with, and let's say that the number one thing that I have here is s equals 6. And what does is equal to 6 mean? It's the total wealth between us. So if I had two to begin with, that means the other person had $4 to begin with. And now you could just have this chart wherein, let's say at time one, I went here, so I went to $3. Then I could have gone another one. So let's say I just stopped at five, and then I could have just gone slightly down, slightly down, slightly down. So you can still continue to play this game, but you have no idea how many time steps they're going to be because it just completely depends on what the last case was. And as soon as, let's say, if I get here, the game stops, right? The game stops. But it's almost impossible to predict how many time steps there are going to be, which is why we just think that, oh, this is such a complicated game. But then there are a couple things that we just think about in a deeper sense, and I'll now just, okay, that looks like a mouthful, but it's telling us exactly what we've already done. It's telling me that what's the probability that at time n plus 1, I have wealth k plus 1. So this is my wealth at k plus 1, and I started with k at time n. So what does that mean? It just means I won a draw. So what is P telling me? It's telling me I won at time n. And it's the probability of me winning at time n. That's all it's telling me. Very similarly, I can look at the probability of myself losing that draw given that I began with k dollars. What's the probability of that? It's just q. So it's that I lost at time n, and it's just the probability of that, right? It's just the probability of me losing that game, and this is my wealth at time n plus 1. This is what I started with, right? And yeah, that's how you look at them. That's how you just sort of compute these.